Okay, we're going to work on some power series and find values of x for which we have convergence. Now, we're going to use the ratio test because every term does not have the power n. It's only in two terms. So we're going to use the ratio test. Now, replace n with n plus 1. And now look at the ratio. So be smart. Don't divide. Multiply by the reciprocal of an. And, of course, we have to have this in absolute values. Okay. So at this point, again, as before, we're going to use algebra. Ten to the n times 10, x to the n times x. And that's pretty much it. The 10 to the n's cancel. The x to the n's cancel. And let's keep track of what we really have here. We have a 10, we got an x, we got n cubed, and we got n plus 1 cubed in that absolute value. So we have the absolute value now of 10, 10x, n cubed, really over n plus 1 cubed. So by properties of absolute value here, I'm going to use the product rule. That we've gone over for absolute values. The absolute value of a product is product of absolute value. That's what we're using to really separate that variable x over here that you see here. Now, all the terms that you see here are positive because n is natural numbers. So I can get rid of the absolute value for this portion. 10 n cubed over n plus 1 cubed. And I can actually write the portion that has, I should say, the 10 using properties of exponents. I'm just going to rearrange the order. And this is pretty much what we're looking at. So now we're going to look at the limit as n goes to infinity of the absolute value of an over an, which would be the limit of 10 n over n plus 1 cubed, the absolute value of x. So because this limit applies to the variable n only the variable n, it's going to apply to these terms. The other terms I thought of as constants. So they come out. 10 absolute value of x, the limit as n goes to infinity of n over n plus 1 cubed now. All right. So this portion goes to 1 because as n gets big, n over n plus 1 goes to 1, and you're really going to cube that portion. 1 cubed is 1, so this limit is 1. So we have 10 times the absolute value of x. So I didn't do this earlier, but maybe I'll do it now. I'm going to copy this portion here. to emphasize what's happening here. That by the ratio test, we require that this limit here be less than 1 for convergence. So this portion has to be less than 1 so that we have convergence here. What that means is 10 times the absolute value of x should be less than 1, which means the absolute value of x is less than 1/10. And by definition, this is 1/10 less than x. I should say negative 1/10 less than x less than positive 1/10. This is the interval of convergence. This is what we're looking for. However, we have to note something. We're looking for the interval of convergence here. That when you looked at this portion of 10 absolute value of x, remember when that portion is bigger than 1, we have divergence. So it's going to diverge for those values. It is inconclusive when we set this portion equal to 0. So inconclusive means it may converge, it may diverge. We just don't know by the ratio test. So this is inconclusive now. All right, well, solving this equation, because it's an absolute value equation, means we have the absolute value of x is 1/10 by solving for the absolute value. That means two things again. That means x is positive 1/10. It means x is negative 1/10. So we're going to have to check these values for the original series here of 10 to the n, x to the n, n cubed. So this is the series. 10 to the n, x to the n, over n cubed from 1 to infinity. We got to plug in these values and find out whether this converges or diverges here. So we're going to replace this x with 1/10. So you're going to end up with the series here, 10 to the n, 1/10 to the n over n cubed, which gives you really 1 over n cubed. And we know this is a convergent p-series. So this is a convergent p-series. This converges. You got convergent p-series because the p-value is the power here. Any power bigger than 1 is convergent. So we know this already. So when x is 1/10, we get convergence, which means I can include in the interval, which is what we're looking for here, this interval of convergence, we can include the 1/10. Go through the same work with x being now negative 1/10. So we're going to plug in that x being negative 1/10. Very often we'll just say, okay, this case, x is positive 1/10. This case, x is negative 1/10. So we get the sum 1 to infinity, 10 to the n, negative 1/10 to the n over n cubed. So let's dive in a little deeply here into the algebra portion and kind of take a look at what that means, in case you were wondering. 10 to the nth, if I distribute my power, if I see this as a product, negative 1 times 1/10, and I distribute the power n by properties of exponentials, that'll give me, again, 1 over 10 to the n. Essentially, it's just going to be negative 1 to the n. So this series is what we get when we replace x with negative 1/10. Now, this also, by the way, converges by the alternating series test. You guys can actually verify that. So when x is negative 1/10, we also get convergence. That convergence will be by the alternating series test. So the answer here for the interval of convergence is that, yes, it's between negative 1/10 and positive 1/10, but it also includes the endpoints. So as an interval, a formal interval, by the way, sometimes we look at this as, if it lets me write down properly, we're including the endpoints. All right, this is what we're looking for, the interval of convergence, because these are the values of x we care about for this series. Remember, this defines a function here. All right, that's number 5. Now, number 6 is almost a root test. The real issue is right here. This is not n to the n, so we can't use the root test. It's going to be the ratio test again. So we'll put down, we'll list this as an, and we'll use the ratio test. An will be 10 to the n, x to the n, and 3 to the n. An plus 1 is 10 to the n plus 1, x to the n plus 1 over n plus 1, 3 to the n plus 1. So looking at this ratio again, be smart in a sense that write this as a product, not a quotient. So you're multiplying by the reciprocal of a to the n, which is n 3 to the n over 10 to the n x to the n. So now, again, this is an absolute value. You're essentially using some beginning algebra and a few properties of absolute value, and then the limit. So, okay, 10 to the n times 10, x to the n times x, and that looks like that's the only algebra. Oh, down here, 3 to the n times 3. Okay, we can do more. So let's start our cancellation here. And now let's see what's left. 3 to the n goes away. Okay, let's be careful here. 10 is left, the x is left, the n is left, n plus 1 is left, and 3 is left. So we got to be very, very careful to see what is actually left here in the absolute value. 10x n. And I'm going to just change the order of those numbers. All right. So again now, by properties of absolute values, by the product rule we've seen prior, I can pull out or simply separate my x, but I have to use the absolute value here. These terms are all nice and positive. So you're going to get the absolute value of x times 10n over 3 n plus 1. Okay. 10n xn 3 to the n. Alrighty. So now we're going to apply that limit. N goes to infinity. The absolute value of x, 10n over 3 n plus 1. Let's make sure there was a 10 there. There was a 10. All right. All right. Well, okay. So the limit as n goes to infinity applies only to wherever there's an n. We got the absolute value of x and 10/3 as constants. We can pull that out. 10 absolute value of x over 3. Pull out your constants, n over n plus 1. Now, this limit that we see here come on, we're going to want to add a page. That's all we're doing. This limit here goes to 1. So let's again take a deeper look at what's happening here. That applying the limit to the ratio in absolute value we get is really equal to (10) absolute value of x over 3. And in order to have convergence, that needs to be less than 1. That'll give us convergence here. So solving for the absolute value now is actually 3/10. And the definition of this absolute value inequality, or values of x between -3/10 and +3/10. So ladies and gentlemen, this is essentially what we're looking for. This is our I in the interval of convergence. However, I'm not going to write down the divergence case like I did before. We're just going to note that when 10 absolute value of x, okay, let's do that, greater than 1, yes, you get divergence. So this is all the other values. Let's be very clear. However, 10 absolute value of x over 3 equals 1. That's the inconclusive values of x. Inconclusive. May converge, may diverge. So doing some algebra, and I'll change colors. The absolute value of x is 3/10. This is an absolute value equation. And solving an absolute value equation means x is -3/10. We got to check that. And x is +3/10. We got to check these two values for x in our original series to see if it converges now. So go back to the original series here. 10 to the n, x to the n, and 3 to the n. 10 to the n, x to the n, and 3 to the n from 1 to infinity. So let's try working with x is -3/10 first. Plug in a -3/10 here, ladies and gentlemen, for x. You get the summation of 10 to the n, -3/10 to the n over n, and then 3 to the n. Now, using some algebra, you get -3 to the n over n, 3 to the n, and using some more algebra in the sense that -3 to the n is actually -1 to the n times 3 to the n. So -1 to the n times 3 to the n over n times 3 to the n here. So the 3 to the n cancels, and what you're left with is the very famous alternating harmonic series that converges by the alternating series test. So this is a convergent alternating series by the alternating series test, and we know that happens when x is -3/10. So we can include negative 3/10 here in the interval I of convergence. We're going to now do the same with x being positive 3/10 here. So we're going to now change that to a positive 3/10 for x. Plug that in. And let's see what happens. Let me copy this here. We need another page. All right, doing some algebra now. Plugging that value in, we get 10 to the n, 3/10 to the n over n, 3 to the n. Algebra. This is 3 to the n over 10 to the n over n, 3 to the n. As you guys can see, this term goes away and this term goes away. You really end up with the very famous divergent harmonic series. That's 1 over n, and that's the very famous divergent harmonic series. So what does that mean? It means we could not include in the interval of convergence the value of x being 3/10. So you got what's called a half open, half closed interval here. This is what that looks like in terms of interval notation. We include the negative 3/10, but we don't include the positive 3/10 value in the interval of convergence here. This is what we're looking for. All right. Let's continue to do some more. We did these earlier. Let's look at number 8. And we're going to have to use the ratio test. Negative 1 to the n, x minus 3 to the n over 2n plus 1. Okay. Now, the next term, we just replace n with n plus 1. So let's be careful here, because I'm going to do a little bit of the algebra here now. Just going to distribute. Replace your n with n plus 1. So that'll be 2n plus 2 plus what? 1 gives you 2n plus 3. Combining like terms and just doing a little bit of that algebra down here. Okay. All right. This is a to the n plus 1. We'll do that right now. So the ratio of a to the n plus 1 over a to the n will give you negative 1 n plus 1, x minus 3 n plus 1, 2n plus 3 times the reciprocal of an. We can write it as a quotient, but we know that's going to give us an extra step. So we're going to be smart again about our arithmetic. This is all in absolute values. Okay. What I've been saying at this point, let me move it down a little bit, is we're going to use some algebra over here now. You got algebra to use. Here's some of that algebra. Negative 1 to the n, negative 1. X minus 3 to the n, x minus 3. And I think that's it. So we can do some cancellation now. Negative 1 to the n, negative 1 to the n goes away. X minus 3 to the n, x minus 3 to the n goes away. And that's about it. So let's go back and see what is left very carefully here. Okay. So what is left now? Negative 1 x minus 3 times 2m plus 1 over 2m plus 3. All right. Now, using properties of absolute value, you got the absolute value of negative 1, the product rule. I'm going to apply the product rule twice. And you guys can see exactly what I'm talking about. So, you know, if you said, hey, how, you know, what's the deal with this algebra stuff, right? It's just the product rule, meaning if I have 3 terms multiplied together in absolute value, this is what I just used. So just sharing with you guys what's going on now. The absolute value of negative 1 is positive 1. And then all of these numbers here are positive because n is natural numbers. So I'm going to write it this way. You got 2m plus 1 over 2m plus 3 times the absolute value of x minus 3. Okay. That is, again, just this ratio here. Okay. So we're going to apply the limit now. This is the ratio test. Limit absolute value am plus 1 over an. The limit, this is as n goes to infinity. Everything you see here, I'm going to copy it. Okay. Now again, I'm going to emphasize that this is the limit as n goes to infinity. So we're applying the limit here. We can think of the absolute value of x minus 3 as a constant, so we can pull that out. You now have the limit as n goes to infinity. 2m plus 1 over 2m plus 3. So this limit again will be 1. So writing everything down again, I want to emphasize the ratio test. That in order to have convergence again, this limit needs to be less than 1 to get that convergence. What we're saying is the absolute value of x minus 3 has to be less than 1 for convergence. That's equivalent to saying, by definition, I should say, negative 1 less than x minus 3 less than positive 1, and we can solve for x by adding 3 to the left, right, and the middle. You get 2 less than x less than 4. This is what we're looking for. This is that interval I, interval of convergence. Okay. Our interval of convergence, however, I'm going to put the note, and I'll write it down. We know by the ratio test that the limit of the absolute value of x minus 3 greater than 1, for those values of x, we get divergence. It's everything outside that interval. The only thing we have to check is the inconclusive cases. And this is an absolute value equation again. It's inconclusive. All right, we need more space here. So solve this absolute value equation now. I guess this is where it's intermediate algebra. X minus 3 is negative 1. X minus 3 is positive 1. Add your 3. X is 2. Add your 3. X is 4. We got to check these cases. When x is 2 and when x is 4 into the original series, That is a little complicated. Negative 1 to the n, x minus 3 to the n. I'm going to have to keep going back. And plug in those values for x and see what we get. 2n plus 1 there, looks like. I believe that was 0 to infinity. Okay, let's check the cases when x is 2 now and see at the endpoints. What do we get? So when x is 2, plugging that in for x, we get negative 1 to the n, negative 1 to the n over 2n plus 1. Now, this numerator here, doing some algebra, is going to really be positive 1 to the n. Okay, because it's going to be, if you wanted to see the algebra, just properties of exponents. Negative 1 times negative 1 to the n, positive 1 to the n, which is 1. So we get 1 over 2m plus 1. I think that was 0 to infinity. Yeah. Now, this is actually divergent. We've seen something like that in the past. You can use either you could use the limit comparison test or the integral test. We know that series simply diverges here. It's kind of related to the harmonic series. So you can use that limit comparison test or you can use the integral test. This is divergent, and that happens when x is 2. All right, what happened here? So do that weird thing. Now, plug in the value. X is, I believe, 4 now. All right, we're going to plug in 4 here. So go back to the original series. You get 4. The series will become negative 1 to the n, positive 1 to the n over 2n plus 1, which is going to equal simply negative 1 to the n over 2n plus 1. And this here converges by the alternating series test. So it converges. I don't know why it does that. So we got convergence only when x is 4. So we're going to have to include the endpoint only here when x is 4. So really, as an interval, it's the open endpoint 2, closed 4. It's a half open, half closed interval. Include the value for x is 4. This is your interval of convergence now. All right. So what I'm going to do is let you guys do some of these. I'm going to go straight to 9, 10. I think I'm going to go straight to 11. And let's see what happens here. This could be very interesting. Okay, this is something you're probably not used to seeing. So I'll go straight to number 11. And look to apply the ratio test. So it looks like you got an even number. You got a product in the denominator with even numbers, 2, 4, 6. Describe an even number as 2n. The next term, n plus 1 squared, x to the n plus 1. 2, 4, 6. 2 to the n plus 1 term now. So I'm going to do, ladies and gentlemen, a little bit of algebra here. This is 2n plus 2. So I'm going to write the next term strategically, if I even said that correctly. N plus 1 squared, x to the n plus 1 over 2, 4, 6. You're going up to 2n, And then you go up to 2n plus 2. That's really what's happening here for this particular question. So now let's take the ratio of these two. And I'm just going to copy everything here. And don't forget, instead of dividing, we're going to multiply by the reciprocal of an, which will be 2, 4, 6, all the way up to 2n again, n squared x to the n. So let's just look at this in terms of the absolute value now. Okay, do some algebra. And it looks like I could just do this here, x to the n times x by properties of exponents. We're going to use some algebra here. All right. So, ladies and gentlemen, let's get rid of the x to the n here. And believe it or not, this 2 times 4 times 6, all the way up to 2n, this will cancel as well. That's why we wrote it down the way we did. So if we're very careful now, we can go back and see. We got an n plus 1 squared term. We got the x term. We got a 2n plus 2, and we got an n squared term. All right. Not as bad as it looks. All right, so now let me do just a little bit more algebra. This is 2n plus 1, so I get this canceling. There's only one of those terms. You get the absolute value of n plus 1 over 2. It's really x over, let's be careful. It's 2n x. All right. Oops, n squared. All right. Now let's see what we can do. Remember this. By properties of absolute value, this is n plus 1 over 2n squared times the absolute value of x. And all of these terms are positive for the first terms, not the x values. For the n terms, these are all positive. So you're going to end up with n plus 1 over 2n squared, absolute value of x. So, taking the limit now, as n goes to infinity, absolute value of an plus 1 over an is really the limit as n goes to infinity of what we just got by the ratio test. Okay, so I'm going to put every Gore detail and remind you this limit is as n goes to infinity, and here's your n's, so we can see the absolute value of x as a constant. We pull that out. We got the absolute value of x, limit, n goes to infinity, n plus 1 over 2n squared. So what does this limit go to? Well, I can divide by every term by the highest power in the denominator. That's an n squared, n squared, n squared. We can use calculus 1. So we get 1 over n plus 1 over n squared over 2. Really, let's double check. 1 over n. Alrighty. So both of these go to 0. So what is happening is 0 plus 0 is 0 over 2. This limit is 0, ladies and gentlemen. And that's what this is for all x. So we got the absolute value of x times 0, which is 0. Now, 0 is strictly smaller than 1. And if you have to see the detail, let me show you what I'm talking about. Let's go back. Copy that. We showed for all x that this limit is 0. So it doesn't matter what our x value is. This is true for all x values. Now that is smaller than 1. So we get convergence for all values of x. What that really means is every number on the real number line, all x. That's the set notation in a sense. The interval notation is what you see here. Okay, that's the interval notation they're looking for. That's I. So that's kind of what we want to find, ladies and gentlemen. That one wasn't too bad, by the way. I don't know if we should do one more just for the road, maybe. Try this one. For the road, ratio test, an x to the 2n over 2n factorial. The next term, am plus 1, is x to the, let's be careful here, 2 m plus 1 over 2 m plus 1 factorial. So maybe it is good we go over this one as well. I'm going to simplify now. That's x to the 2m plus 2 over 2m plus 2 factorial. All I did was distribute here and here. All right. So the ratio of am plus 1 over an x to the 2m plus 2 over 2m plus 2 factorial times the reciprocal of an, which is 2n factorial over x to the 2n. And we need to see this in absolute values. All right. Now, as we've been saying all along, we're going to use algebra over here. So by algebra, you got x to the 2n here times x squared. And this we can say is 2n plus 2 times 2n factorial. Okay? Let me take that back. And we don't have any space, so it's really 2n plus 2 times, we got to count backwards, 2n plus 1 times 2n factorial. Okay, so the 2n factorials go away, the x to the 2n's go away. Let's be careful and see what is left. X squared is left, and you got 2n plus 2 times 2n plus 1. So we get the absolute value of x squared over 2n plus 2 times 2n plus 1. Properties of absolute value. Or even better, let me just say this. Everything you see here in the absolute value sign is positive. So I can remove the absolute value sign. This is the absolute value of the ratio. So we take the limit now of the absolute value of the ratio, which is the limit of everything you see here. All right. Let's see if we can move this over. So again, n's going to infinity. We can think of this x squared as a constant. All right. All right, thinking that as a constant, let's pull it out. X squared times the limit as n goes to infinity of 1 over 2n plus 2 times 2n plus 1. Okay. So yet again, this limit here goes to 0 for all x values. And we're left with x squared times 0, which is simply 0 here. So what we're saying here is that this limit is the finite value 0, and that happens for all x. Well, that limit 0 is less than 1, so that means we have convergence for all x. Convergence for all x. All x means every real number on the real number line. So as an interval here, this is what they're talking about. We want to find this particular interval. It's your interval of convergence. So anyway, I think I've had enough, and I will send this to you guys, and hopefully you take a look at that and you can see how this works.